Okay, we're looking at have I had any lecture with you in the past?
No, sir.
Okay, my name is Engineer Dr. Ekene Samuel Mbono. I'm from Mechatronics Department. So this course, which is BME what again? Is it 942 or 924? Microcontroller based.
Yes, it's not BME now. It's MD 942 MDE.
MDE. MDE meaning,
Yes, for medical engineering option.
okay, okay. So we're looking at microcontroller-based digital systems. Basically, in
Yes.
this course, we're going to look at the fundamentals of digital systems, and then I will introduce you to a microcontroller that is open source, which is Arduino. If you can program Arduino, then it can form a building block for you to understand how microcontroller works. And then I will also introduce you to Arduino IDE. IDE means Integrated Development Environment. And then we pick up a sample project. The lecture has to be interactive. I will do the teaching today. By next week, you are going, before I continue, you have to do presentation. I will tell you what the presentation is all about, probably about 10 minutes on the areas I will give you. So we are going to have three online sessions. So after today, we're going to have two more online sessions. Where are you residing?
I have for now. But at times I also operate from Enugu.
Okay, and where is she residing?
Abakaliki.
Abakaliki. Wait, so is it the person is it the woman that gave birth to a child the other time?
Yes, yes. During her MSc.
Oh. I don't even know who has been communicating with me. I helped her in her master's thesis. Oh, I didn't know she's the one that had been communicating with me. Oh, Meriwo.
Yes, yes, Shemeriwo.
Ah, oh, Meriwo, have you joined now? Can you hear me now? I can see she's online. Can you hear me? If you can hear me, unmute yourself and talk.
I can hear you very well.
Okay. I did not even know you're the one that had been communicating with me all this while.
Mm.
Okay. So that's how the
I'm the
project
one, sir.
is all right. That's how the lecture will go. We'll look at fundamentals of digital systems, and then we'll look at introduction to microcontrollers, introduction to IDE. I do know IDE is a platform for programming microcontrollers, and then we have to take a sample project. Now, this project is supposed to have a practical component, but two of you are staying apart. Even if we do it virtually, it doesn't make up for the um, practical. As we progress, we know what to do, but if I were to suggest, probably you will find time at least a day, come to IEEE hub at Futo, and at least have a feel of programming Arduino, even if it means lighting an LED or interfacing one of the sensors in biomedical field. That'd be fantastic. Okay, this is my profile. I don't have to read it. You just know that um, my name is Dr. E.S. Mbon. If you get the lecture material, it's being recorded. You can look at my profile properly if that is important to you. You can also check out my Google link or LinkedIn, whatever it is. So let's go to the business. Fundamental of digital systems. Digital systems process, store, and transmit information using discrete values. That is two-state values. It's either 1 or 0, on or off, male or female, low or high. You don't have in between. You don't have in between. If it's an analog system, you can have 0, 0.5, 1, 1.3, 1.31. If it is a digital system, it's either is 0, it's either is 0 or high, it's either is 0 or 1. It's either is 5 or 0. It's either is here or there. There is no in between. I want to believe that you did digital systems at least a little in your undergraduate level. Is that correct?
Yes, sir. Sorry. Is it where we have no gate,
Your voice is breaking.
and gate, NAND gate, and the rest of it?
Okay, you did AND gate, NAND gate, NOR gate,
Yes,
OR
sir.
gate.
Can you hear me? Saying digital system
Your voice is breaking. I'm not hearing you. Augustus, are you hearing her clearly?
about.
No, sir, it's breaking. I think our network is
Yes, sir. Can you hear me now?
Yes. But when you begin to talk now, it begins to shake again. Speak on. Let me see if I can hear you. Maybe you have to change your position. Let's continue. So, I heard that we are talking about.
Hello, can you hear me, sir? You
Yes,
are referring to, is that where we have no?
you are muted yourself. Unmute yourself. You muted yourself. Unmute yourself.
Hello, sir. Can you hear me now?
Yes.
Okay. I was asking, the digital system you are talking about, is it where we have OR gate, NAND gate, and gates?
Yes,
The gate, the
that's part
logic
of it.
gates.
That's part of it.
I think that was the extent we did during our undergraduate days.
Okay. That's part of it, but not the complete part of it. So, even now, we won't be able to do all of them, but at least you have been introduced to a logic state. Now, the digital systems form the backbone of modern technology, driving computers, smartphones, and automation by converting physical quantities into robust, noise resistance, binary signals. Even in the medical field, whatever information we are getting in the analog world, when it goes down to the level of computer, it's either 0 or 1. It's combination of zeros and ones. The study and design of digital system rests on 4 interconnected pillars. Number 1, number systems and codes. We're going to see that today. And then Boolean algebra and logic gates. We're going to see a bit of it. Combinational and versus sequential circuits, that's system, combination versus sequential systems. Hold on. And then circuit system architecture. We are not going to deal with sequential systems. We're not going to go into that. We're not going to go into combinational systems. We're not going to go into system architecture. My interest now, our interest now is to expose you to the information you need to be able to at least have a rough idea how you should be able to implement your system or your project. So we go to number systems and code. Number systems and codes. So computers depend heavily on specific number bases. We are familiar with base 10. Are you familiar with base 2? I suppose because even in primary school, I think in primary school we were taught base 2. Is that correct?
Yes, sir.
Yes,
So
sir.
everybody is supposed to be familiar with base 10 and base 2. So those are the things we need. And then you also need base 16, hexadecimal base. Programmers also use octal base and hexadecimal, that is octal base 8 and hexadecimal, as shorthand to compactly represent large binary strings. Now let's go to business. You can see my screen. Can you see my screen?
Yes, sir.
Yes, sir.
Okay, we are looking at digital map table. How do we generate digital signals? What is the origin of digital signals? When it comes to digital signal or signals, counting starts from 0, not from 1. So we have 0, 1, 2, 3, 4, 5, 6, 7, etc., etc. This is how computer count things. Now, with respect to binary, if it is not this, is that. What is 2 raised to power 0?
1.
1.
So 2 raised to power 0 is 1.
1.
And of course, anything raised to power 0 is 1. Now, at this first column, by the right on this map table, 2 raised to power 0 is 1. That means we are going to be alternating 0 and 1 once. Remember, we're talking about digital what? Systems. If it is not 0, it is 1. So you can see 0, 1, 0, 1, 0, 1. I mean 0, 1, 0, 1, 0, 1. You can see that is the sequence. Is that clear to you?
Yes, sir.
Now we go to 2 raised to power 1 is 2. We begin to alternate every other 2. That's at every other 2 counts. So we have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1 till infinity. We get to the third, or rather the second, because this is the 0 column, first column, second column, 2 raised to power 2 is what?
4. 4.
4.
4. So we are going to alternate how many times?
4 times.
4
times.
4 times. So that's why we have 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1. I just stop at 15. The thing continues. And then 2 raised to power 3 is 8. 2 raised to power 4 is 16. Like that, like that. If you increase this table, after 16, that is after now, after 16, the next value in the third 2 raised to power 4th column will be 1. And like that. This forms the basis of binary counting or digital counting, because you can see clearly that this is 0 is 0, 0, 0, 0, 0. 1 in digital counting is what? 0, 0, 0, 0, 0, 1. 2 is what? What is 2? I want to believe that you people are listening.
2 is 0, 0, 0, 0, 0, 0, 1.
Is that what you see on your screen? What is 2 in digital format based on that map?
2 is 0, 0, 0, 0, 0, 0, 1, 0.
1,
Like
0.
0 6 times.
Okay, Augustus, what is 2?
So I'm trying to see the screen.
You say?
2 is 0, 0, 0, 0, 0, 0, 1, 0.
Good. So we are moving from normal counting now to digital system. 3 becomes 0, 0, 0, 0, 0, 0, 1, 1.
1.
4 becomes 0, 0, 0, 0, 0, 1, 0, 0. And like that, 5 becomes 0, 0, 0, 0, 0, 1, 0, 1. And that is how digital system is counted. You notice that 15 is 0, 0, 0, 0, 1, 1, 1, 1. What that thing means, did that thing means, this is the way your computer, this is the way your phone sees digital numbers. When you take your smartphone and you place it, and probably you press phone, and the keypad comes out. When you place 5, computer doesn't understand what is 5. Of course, that 5 you place there is just an ASCII value of 5. There is a decoder or encoder that decodes that thing, that 5 you have placed, and breaks it down into zeros and 1. And in case of 5, what your phone, the microcontroller that is inside your phone, will see is 0, 0, 0, 0, 0. The last 3 digits there must be, if it is 5 you press, the last 3 digits there must be 1, 0, 1. Do you get the point?
Yes, sir.
Okay. Now we move over to binary coded decimal. Binary coded decimal. binary coded decimal generated from this digital map, but binary coded decimal just have 4 digits. 4 digits. So you can see 0 is 00004. 1 is 0001. Y2 is 0010 in BCD. And 7 is what?
0111.
0111. So anywhere you see is 0111, just know that we are talking about 7. 7. Anybody that will do well in digital system and microcontroller applications will have to be familiar with these numbers, just as you are familiar with your 0 to 9. You must be familiar with these numbers. 9 is 1001, 10 is 1010, 11 is 1011, 12 is 1100, 13 is 1101, and 15 is 1111. Now, in hexadecimal representation, hexadecimal means base 16. In hexadecimal representation, these numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's hexadecimal representation. Okay? And we'll move over to the next slide. So, from if you are going to talk to a computer in binary format, you have to represent depending on the compiler, but most compilers will accept this. If you want to refer to 0 in binary, you have to make it 000 up to 8, and then B there means is you are talking about binary numbers. Binary numbers. These values are just the values generated from here. Okay? 1 is generated from here, but then you have to write them together. From that table, you get your hexadecimal value. 0, you have to divide it into 2 and then use binary coded decimal to convert them to hexadecimal value. 0 is 00H, 1 is 01H, 02H, 03H, 05H, up to 15, which is 015 is 0F. You can see. Can you see where I highlighted?
Yes, sir.
Yes, sir.
So that 000 in binary coded decimal is 10. Then 1111 in binary in BCD is F. And then we'll change the B because we are no longer dealing with binary, and I change it to H. So you have converted that number to hexadecimal. This, in fact, anybody that is not familiar with this, then the person is not ready to flow with digital systems. Is there any question so far?
Yes,
My
sir.
hand
I
is
want to
raised.
ask.
Go
Hello?
ahead.
Yes, I said I want to ask concerning getting familiar with these numbers. I know, like the ones we learned, that how to solve, how to convert those ones. But for these ones that are
Oh,
more like maybe low
hold on,
level,
hold on,
how do
hold on.
we?
I want to connect with my smartphone. At times, this computer audio is not all that
Okay.
fantastic. Uh,
In progress.
okay, ask your question.
Okay. So I'm asking. I said, are we to memorize this? This this is more like maybe a log table. Getting familiar with them. Is there any maybe method, or is there any way we can get used to it, or we just get used to it by using it?
The best way to get used to something is by using it, but I know that you guys don't have time. But the way I get familiarized with this thing is by using them consistently.
Okay. Okay.
But you can study them, at least for your exams, you should be familiar with them. But the best way to get this thing into your bloodstream, if I should use that word, is by using them to do practical stuff. I have done a number of projects, so I'm not trying to memorize them. They are in me already. But for
Okay.
the purpose of exam, you have to read them now, at least get them into your head.
Okay. Okay.
I want to ask a question though.
Go ahead, I can see your
The
hand.
the hexadecimal numbers, the like 00H, 01H, the H there, is it just representing that is a hexadecimal number, or does it represent anything apart from that?
Yes, it represents hexadecimal numbers. When you give it to a compiler that compiles your program, it will be able to interpret it as a hexadecimal value. Otherwise, it will
Okay.
interpret it as a decimal value. It will not treat it as
Okay.
base 16. It will treat, if you remove that H, computer will treat it as base 10.
Okay.
Okay.
Okay, sir.
Okay, so we move on. Now we are still in number systems. We're looking at digital terminology. So in digital systems, we are talking about if it is not this, it is that. You are dealing with two things. If you are dealing with human beings, if somebody gives birth, if it is not a male, then it is a what?
Female.
It's a female. Uh, um, um, so if you are dealing with digital systems, if it is not high, then there is no other option. If it is not high, then it's low. If you take your multimeter and the system is digital, if you place your meter there, if it's microcontroller based system, if it is not zero, then it will be equal to VCC, depending on what the VCC means. If the VCC for that microcontroller is 3 volts, whatever you'll be getting on that circuit will be either 0 or 3. If the VCC for that microcontroller is 5, if you measure any point on that circuit, on that system, if you didn't get 0, then you will get 5. That is not, you won't get anything in between. Once you begin to get anything in between, then it is no longer a digital system. It's either you are not dealing with a digital system or something has gone wrong in that circuit. So if it is not on, it is off. If it is not 1, then it must be 0. You get the point? You can see can you see my cursor?
Sir.
You can see my cursor. Can you see my cursor?
Yes, sir.
Okay, so you can see this is a logic. The one in blue is logic 0. This one in red is logic 1. So logic 1 will turn on an LED when properly biased, while logic 0 will put it off. So this LED can either, just as it's presented in this circuit, can either be 0, it can either be high or low, it can either be on or off. There is no sitting on the bench. Concept of digital systems. Digital signals represent information using discrete values, typically binary code of zeros and ones. Unlike analog signals that vary continuously, digital signals transition between defined voltage or frequency levels, like a square wave. This allows for highly reliable processing, easy encryption, and greater resistance to noise. So the fourth diagram here, you can see my mouse. That is analog. It can vary, it just vary. But here, you can see it moves from this point. Here is 0. This is just high. When you want to transist, it transits back to 0 in a straight line. You move to this point, goes back to high. This is a kind of a wave, square wave or rectangular wave. So that's what the digital system is all about. If you are going to measure the pulse rate of your heart using a sensor, yes, the sensor will give you an analog signal. But analog to digital converter will convert it to discrete values, which the microcontroller will accept. ADC. ADC converts this analog signal to digital signal for microcontroller applications. Now, remember we said there are 4 pillars. There are 4 interconnected pillars on which digital systems rest. Number 1 is number system and codes. The second one is Boolean algebra and logic gates. And incidentally, have done a bit of logic gates just to refresh your memory. AND gate is a fundamental logic gate that produces a high when all the inputs are high. At this level, we are not just talking about AND gates. We should be thinking of application of AND gates. Applications. What are the practical applications of AND gates in biomedical engineering? Another way to put that question is, what are the practical application of AND logic in medical engineering? Is something you have to find out. So this is the symbol of AND gates. This is the truth table. When any of the inputs is 0, then that root must be 0. Okay? And then this is the Boolean representation. Y is the output. Y is equal to A and B. The dot sign is used to represent AND. So let me ask you, can you give one practical application of AND logic in medical or biomedical engineering? Yes, I'm waiting to hear from you. Just give us
one practical.
Go ahead, I'm listening. We're listening. It's like your network is not steady there. Your network is not steady there. I'm not hearing you. Augustus, if you're hearing her, you can indicate, but I'm not hearing her.
Application, I can say in the.
Your voice is breaking.
Hello, sir, can you hear me now?
Yes.
Hello?
Try to talk now. Yeah.
One practical application I can say is in electronic systems, electronic circuits.
Electronic
I
circuits,
don't know
like
if
what and what now?
Mhm. Like digital blood pressure monitor.
You don't really say the application of AND logic there. The AND logic.
Okay, so let me make an attempt.
Okay.
Like maybe in alarm, just like you mentioned about like monitoring, like when you want to monitor like in a device, let's say patient monitoring now. So that and logic can be applied in alarms, so that maybe that when a particular physiological parameter is high, then maybe the alarm will be activated, maybe something like that.
Okay. So yeah. Even though you didn't narrow it down to a clear example. But let's assume that you are designing a critical health monitoring system. What are the parameters that need to be monitored? Or what are the parameters that when they are above normal threshold, above or below normal threshold, we can say that a patient is in critical condition?
Okay. Even temperature is one of them.
Okay, temperature,
And
yes.
the
Yes.
SPO2, pulse pressure.
Eh? You
Yes.
mentioned temperature.
Pulse pressure,
Yes.
Okay, pulse
Blood
pressure,
sugar.
blood sugar.
pulse pressure, oxygen saturation pressure.
Yeah,
Oxygen sat
your network is disturbing you.
SPO2.
So you can see, I think
Then,
we're getting close to that now. So if before we declare a patient
blood
that, that a patient needs emergency attention, we can say the blood pressure will be high or low, and so and so. Of course, in case of if the what do you call it? The blood pressure is made up of two components. Is that correct?
Yes, sir. The diastolic and systolic.
So for you to declare that patient's in a critical condition, you have to measure the two. And possibly this one is outside normal. The other second one is also outside normal. Once two of them are outside the normal range, you now know that there is a problem. There's a problem. Okay. Some of these things, they are there, and we're just considering one gate. One gate. There is also not gate. We just considered and gate. There is not gate. Something like the temperature of a child is above 37 degrees centigrade. It has passed 37, it's hitting 39. You know, if nothing is done, that child is likely to suffer convulsion. True or false?
true,
Hello?
sir.
When the
True,
temperature
sir.
of a child exceeds 37, the mother must do something. Need to rush that, get that child to hospital so that
Yes, sir.
they have to do something to bring the temperature down. Because if you leave it at that level, if it's in the midnight, you can't get to hospital, then have to be awake, get cold water, and begin to monitor that child, begin to use towel and massage that child until the morning comes. Because if you don't do that, when the temperature hits about 38, convulsion comes. I know what convulsion does. Convulsion, the brain of the children are very delicate. If you are not careful and convulsion comes in, it can affect the brain formation. So that child will grow up not being at his or her best. That is one of the dangers of convulsion. I pray none of our children will have convulsion in Jesus' name. So now that's a practical application of this gaze. In programming now, you notice that you are not just dealing with physical components. Some of these things will be translated to codes. As we are going to see later, I'm going to give you assignment on that. If you read this, you read that, you write a code, a software that will compare the two, and then say what should be done. We are talking about a Boolean algebra and logic gates. So we are at OR gate now. OR gate is an OR condition, either this or this. either this or this. It's a fundamental digital logic circuit that outputs a 1 that is true or high if any of its inputs are true. That is, if any of its inputs is true, it only outputs a 0 if all of its inputs are false. So it performs logical addition. When you look at the truth table will only be 0 when all the inputs are zeros. So when you think a little, you can come up with a medical condition that might be all in nature. If a lady has a genotype of AA, for example, then she can get married to a man who is either AA or AS. Should we include SS? Of course, if she gets married to a man that has SS, the children, based on scientific fact, the children won't have any issue. Is that correct?
Yes, sir.
The children won't have any issue. The only challenge is that SS people are prone to sickness, and they live. Every one of us live by the grace of God anyway, but their life is just cannot be. I don't know the advances in technology now and medicine, whether they have gotten the cure for SS. But then, the much I know, when I was little, anybody that is SS, at times when that thing comes up, they can it takes time to recover. And I know that it's not, based on what I know now, it's not just giving birth to a child that is the issue. It's being healthy and alive to train the children in the way they should go, both financially and mentally and spiritually. So if a woman is AA, then she can get married to either AS or AA. That is an all condition. Then you can, when you think a little, I want you to Google these things. The first one, Chi Emeliwo, right? You will give,
yes, sir.
You will give next week. You will 5 minutes presentation on practical application of AND logic in biomedical engineering. Why Augustus will give 5 minutes presentation on practical application of all logic in biomedical engineering. And finally, before we talk about this, you see, we have just talked about logics. In the real-life implementation with respect to microcontroller, we are not going to pick AND gates or gates. No. We are going to translate them to programs. And there are basic control programs that you need to, or control logics you need to take note of. One is if statements, while the second one is for loop. We call it for loop. The third one is while loop. You have while. In while loop, you have do while, and you have while do. You have while do. You have do while. I just call them while loop. And then you have case statements. So what we are going to do is that Chi and Mediwo will take on if statements if statements and for loop, while Augustus will be presenting on while loop and case statements. So you have 3 things now, 5 minutes. So when we come back next week by the special grace of God, for the first 30 minutes, we'll be making presentation on PowerPoint. On PowerPoint. The first assignment, which is this, and then second one, third one. So 5 minutes. 5 minutes. When you are done with that, then the next lecture will be on introduction to Arduino Uno microcontroller, which you use Arduino in your masters. Is that correct?
Yes, sir.
Yes, sir.
Okay, so we'll look at it, we'll look at the architecture, we'll look at the programming, we'll look at what do you call it? The IDE. You really have to do something meaningful with that. Possibly we get one sense of, but when we come next week, we will